All right, in 5.5, a couple of objectives to talk about here. We want to talk about the derivative of the natural log function, the basic one, natural log x, and also then generalize it to what if we have something more complicated than just x? What if we want to do the derivative of ln of something complicated, or at least more complicated than x? Then we're going to review log properties and apply those to functions before we do any calculus. And that'll help us to make the calculus part a little easier in certain cases. So let's start with trying to figure out what natural log x's derivative looks like. We're going to use a graphing calculator for this, so if you don't have one, hit pause and grab one. And we're going to fill in this table for the function y equals natural log of x and its derivative. That's the key part. So if you don't remember how to do, especially the derivative part, I'll go over that here. If you're okay with it, you can jump ahead, but you should at least try it yourself to get the review of how the calculator works down. So I'm going to graph natural log x, go to y equals to get the graph, and type in ln of x. And if I want to graph it, of course, I hit graph. If I want to fill in the y column, then probably the easiest thing to do is go to table set, which is second F2. Yeah, I want to count by ones, so I'm good there. I'm going to go actually look at the table. I'm going to hit second F5 and hit table. And there it is. And I can just sort of copy down what I got. Oh, shoot, I'm supposed to get a half. Fine. Back to table set. We'll count by halves. And then go to second F5. So at 0.5 we get like a negative 0.693. At 1 we get 0, and so on. I can just kind of highlight some things I need. That's not the hard part. The harder part, or at least the harder part to remember, is how do I go about getting the derivative values? So you go back to y equals. To get the derivative, I want to do, under math, go down until you get to the numeric derivative. And this function is usually designed for finding the numeric derivative at one specific x value. These calculators will not give you the functional derivative. But you can get a picture of the functional derivative. It just won't give you the equation for it. So the way you get the functional derivative is type, first of all, the function you want to differentiate. So I could really literally just type in ln of x over again. Or if I want to be stubborn about it, I can go to variables, y variables, functional variables, and y1 is also ln x. So again, if you didn't want to go through the menu, you could just type in ln x over again. Then I'm going to do comma x. That means in terms of x. And then normally you do comma, the number you want it to evaluate. But here I want the graph of all the x values, so I'm going to do comma x again. And I don't really need to even graph it. I can just go right to the table. Now I've got a column with my y values that I've already used, and I've got a column with my x values. I can see that when x is a half, the derivative, the y2 column is the derivative column, is 2. When x is 1, the derivative value is 1. At 2 you get 0.5, also known as a half. At 3 you get 0.3 repeating, also known as a third. When x is 4 you get 0.25, also known as a fourth. When x is 5 you get 0.2, also known as a fifth. So, you don't have to be a professional investigator to know from pattern here. The derivative of natural log x is simply the reciprocal of the x value. Flipping a half gives you 2. Flipping 2 gives you a half. Flipping 3 gives you a third. So we could just call this 1 over x. So ln of x, which is like a transcendental function, it's this always generates all these irrational numbers, has a fairly straightforward derivative. It's kind of cool, I think. I'm editorializing. I'm sorry. I'm not. to generalize this, to get the derivative of something more complicated than x, you still do 1 over u, but then you have to chain on the derivative of u. So this is a perfectly valid way of thinking about it. A quicker way of thinking about it, kind of a nice, easier to remember trait, is just to take u prime over u. So whatever the derivative of the log quantity is over the actual log quantity itself. Alrighty. A quick review of it's natural log, but log properties in general. You probably first saw back in Algebra 2 and then dealt with a little bit last year, and then went, a year between each time before I even thought about it. And now it's been another year. So let's review these real quickly. Y equals ln x. Keep in mind your subscript for natural log by definition is base e. Log base e, they never really write, they just call it ln. But if I were going to write this exponentially, I would say blank to the blank power equals blank. So I start with my subscript, that becomes the base of my exponent. I cross the equal sign to get my exponent in, if I write it in exponential form. And then whatever your quantity is here is what all that equals. So this is what they call written logarithmically. This is what they call written exponentially. The domain of the function y equals natural log x. Look, you can't put a 0 in for x. ln of 0 would imply like e to some power equals 0 if you wrote this exponentially. E is your base to the x equals 0. E is a number that's greater than 0. No matter what power or negative power you send it to, even if you send it to like negative 10 gazillion, you'll still get like 1 over e to the 10 gazillion, which is still a sliver above 0. So you can't have 0 in your domain of natural log. You can have anything bigger though, so x has to be greater than 0 in order to make this work. Natural log of 1, or quite frankly, any log of 1, doesn't matter what your subscript is. A to the 0 power is going to be 1, or here e to the 0 power is what gives you 1. Anytime you have log anything of 1, you're going to get 0 for a result. A natural log, or any log where you're multiplying a quantity, you can split into 2 terms using additions. This is like natural log of first factor plus natural log of second factor. And conversely, if you have natural log of a over natural log of b, you can split those into 2 terms using subtraction. So basically whatever's in the numerator will generate a positive natural log term, and whatever's in the denominator will generate a negative natural log term. And finally, reminiscent of the derivative's power rule, but for a whole different reason, natural log of something to a power, if you want, you can take that power and write it out front as a coefficient. So this is a handy way of getting exponents down from, getting variables out of exponents when you're trying to isolate variables that are hiding up in the tree. You cut down a log. So the n comes down front, and then you just have natural log of a as a result. In this next problem, we're actually going to apply the idea of differentiating a natural log. You could do this 2 different ways. You could first, I suppose, you could apply log properties. That would be the quick way. Let's do that first. Before I do any calculus at all, I'm going to apply that last log property we talked about. I'm going to bring the power down as a coefficient and leave the rest as is. And then if I need to get y prime, here I have a constant, that'll just stay 3, and I'm going to focus on differentiating this. Derivative of natural log x, we can think of this as u prime over u. So the natural logs, the quantity's derivative, I should say, is 1. And the quantity itself is x. So u prime over u in this case is the derivative of x over x, which is 1 over x. We get, no matter how you look at it, you get 3 over x. If you didn't apply the log property first, that's okay. Oops. You can still get the derivative using u prime over u. It's just in this case, u prime, the derivative of this, is 3x squared, and u is x cubed as is. So the derivative now, or simplifies, to simply 3 on top, and if you cancel out the x's that you can cancel out, you end up with just an x on the bottom. It doesn't matter which method you use, you should get the same correct answer. All right, another example here where we're going to have to differentiate something that has a natural log in it. Now this one's a little bit more complicated because if you take a step back, I mean the function we're given here is a product, which means its derivative is going to be gotten with product rule. So if I'm going to do f prime, I'm going to start with, I guess we could do the second thing as is. So ln of x is the second factor. I'll start with that. Then multiply by the derivative of the first thing, which is u2x. Plus, then I'm going to take the first thing as is, which is x squared, times the derivative of the second. And derivative of ln x is simply this thing's derivative, 1, over this thing as is, which is x. And all we got to do is clean up shop a little. This is 2x ln x. And then x squared over x would just be x. Perfectly valid way of writing the answer. Sometimes if you check answers somewhere, they might like factor out an x, and that freaks people out all the time. Or they'll do something really exotic like put the 2 back up top using the log property that we talked about in reverse. They'll get like ln x squared plus 1. And people are always going, what the heck? I got the wrong answer. Like, nah, no you didn't. You just got a different equivalent answer. Let's look at D. All right, this notation means find the derivative, plug in 1 for x. Now I'm guessing we're also going to have to plug in something for y, but they don't tell us what that is. Fortunately, we still have the parent equation here. We can plug in 1 for x here and see what we get for y. Doing that would mean 1 equals natural log of 1y. Writing this exponentially means e to the first equals y. So y would equal e. So when we're all done getting the derivative, we're going to plug in 1 for x and e for y. Now let's get the derivative. This is going to be an implicit situation because we're not going to, we might be able to isolate the y. Even if we were, it'd be ugly. Let's just jump in and start differentiating stuff. X, when you differentiate it, simply becomes 1. Differentiating over here, we're going to need to do u prime over u to get the derivative of a natural log function, or natural log equation. So u prime is the derivative of xy. That's going to require use of product rule. And then the bottom is just xy as is. I could put that in right now. So the product rule, the top, we're going to start with the second thing as is. That's y times derivative of the first thing, that's 1. Plus, now we're going to come back the other way. We're going to take the first thing as is, that's x, times the derivative of y, which is literally dy over dx. Derivative of y is not 1 when your independent variable is x. But we can plug in all the stuff that we know. We know that y is going to be e, times 1 is still e. We know that x is going to be 1. On the bottom, xy is 1e, which is just e. And all we have to do now is isolate the dy over dx. So I'm going to multiply e over, oh my goodness. So I multiplied e over, and now I'm going to subtract e from both sides, and lo and behold, the derivative is 0 at the specific point 1 comma e.